Okay, graphs of polynomial functions. The basic polynomial shapes are we're talking about the simplest form, and we're talking about situations where we would have f of x equals ax times to the power of n, where a is a constant and n is non-negative. So we want to remember some specific things about them. First of all, polynomial functions of odd degree, their general shape is going to look like this, where it starts at the bottom left, so basically in the third quadrant, ends up in the first quadrant. That's when a is greater than 0. If a is less than 0, then it's going to end up in the start in the third quadrant, or the second quadrant, end up down into the fourth quadrant. Okay. Those are odd degree. If they have even degree, then they're going to look like these, that they're going to either, graph is going to open up so it smiles, or it opens down so it has a frown. Okay? That's when we're talking about just ax to the power that's even. Just talk about some general properties. Continuity, remember that all polynomial functions are continuous, which means that there's no breaks in the graph, there's no jumps, there's no gaps or holes. We're going to talk about end behavior, and end behavior says what's happening as the values of x get really, really big. So get closer to positive infinity, closer to negative infinity. What's happening on the ends? Is the graph going up, or is the graph going down? And that's all going to depend on what we're talking about as far as like leading coefficients and degree. So end behavior of polynomial functions. When the absolute value of x is large, the graph of a polynomial function closely resembles the graph of its highest degree term. So if you have something with a whole bunch of terms, what happens on the end is basically determined by just the leading coefficient and the degree of that first polynomial. So here we have a little table. It has some graphs in it that talks about end behavior, or talks about what's going to happen with the graphs as absolute value of x gets really large. So if we have an even degree, and this plus LC means a positive leading coefficient. Okay? So even degree, positive leading coefficient. On the ends, okay, the graph is going to go up. There could be a lot of stuff that happens in the middle here. So a lot of stuff that happens that can happen in here, okay? But when we talk about the ends, it's going to go up on both ends. Right? So even if there's a whole bunch of stuff here or not anything there, on the ends the graph is going to go up. Even degree, positive leading coefficient. If the degree is even but has a negative leading coefficient, then the graph is going to go down. So basically we're talking about a reflection over the y-axis. So if it's an even degree of negative leading coefficient, that graph is going to be a reflection compared to even degree positive leading coefficient, where even degree positive, they go up, even degree negative, they go down. No matter what happens in the middle, it's what happens on the ends. Okay? Over here we have odd degree positive leading coefficient. Odd degree positive leading coefficient, it's going to start down here in the third quadrant, and it's always going to end up in the first quadrant. Always. There could be a lot of stuff going on here depending on the degree, okay? But when we talk about the ends, they're going to go to negative infinity on the left to positive infinity on the right. Okay? As you can see that in both these graphs. And if it's an odd degree but a negative leading coefficient, then it looks just the opposite. Starts in the second quadrant, ends in the fourth. Second, ends in the fourth. Right? A lot of stuff going on here, but it's going to start up here in the fourth quadrant at positive infinity, come down, do a bunch of stuff, and then end up down in negative infinity. X-intercepts, the graph of a polynomial function, has one y-intercept, which is equal to the constant term, so it could be 0, and it has at most n x-intercepts. So if it's a fourth degree, it could have 4 zeros. If it's eighth degree, it could have 8 zeros or 8 x-intercepts. All right, and a little reminder about something we talked about before was multiplicity. That multiplicity depends upon the degree of the factor of the polynomial. Right? So for instance, in this example right here, they have x plus 3 squared, x plus 1, and x minus 1 cubed. Right? So the degree of the factor tells me the multiplicity. So this x plus 3 squared that has a 0 at negative 3 has a multiplicity of 2 because it has raised to the second power. Negative 1, okay, x plus 1 has a 0 at negative 1, multiplicity of 1 because it's to the first power. X minus 1 cubed has the zeros at 1, multiplicity of 3. Now, when you're looking at your graph, how you can tell this is if its degree is even, right, it touches the graph, looks like a quadratic function here. If it's 1, it's going to just go right through the graph like this one does here. Just goes right through the x-axis. And if it has its odd but greater than 1, then it's going to look like this one here at positive 1 here, where it bends when it goes through the x-axis. So it says if k is odd, the graph crosses the x-axis at C. If it's even, the graph touches. Okay, so odd is going to go through, even it's going to touch. If the odd is greater than 1, it's going to bend like this one does. Okay. All right, so I have a few questions here that I want you to answer. First of all, give your answer to that, so you're going to think about them for a minute. I'm not going to go over them. But I will talk about D for just a second. It says, which of the following functions do not have an x-intercept? And letter A, it does, because I can factor this into, I could write this as x plus 3 times x minus 3. So these has 2 x-intercepts. X squared plus 9 does not, because the graph of that looks like this. It's been shifted up 9 units. So anytime it says x squared plus a number, there is no x-intercepts there. It doesn't cross the x-axis. All right, example 1, we just talked about the multiplicity. So here I have this function here, x minus 4 squared times x plus 3 cubed times the quantity x minus 1. So what you should do is, when you're talking about multiplicity, is make a graph, and then from that, or make a table, and with zeros, what the graph looks like, and the multiplicity to help you with it. So we're looking for, with multiplicity, we're looking for, okay, does it touch? Does it go through? Does it bend? So here's our zeros then, are at 4, negative 3, positive 1. Now the graph for these, if I drew a graph, I have zeros at positive 1, positive 4, and over here at negative 3. And so first of all, we need to look at the degree. The degree of this is 2, 3, and 1 is 6. So when I'm all done, my multiplicity's got to add up to 6. Since this is a 6-degree polynomial, has a leading coefficient of 1, that means that on the ends, this graph is going to go up here and up there, because it's even degree, positive leading coefficient. So here's what this graph's going to do. At negative 3, it's cubed, so the graph is going to come down here and bend there, because its degree is odd, so it goes through. At 1, it's just going to touch, so the graph comes down, then goes through at 1. And then at 4, its degree is 2, so that means it's going to come down here and touch the x-axis and then go back up. So that's basically what my graph looks like without any y-intercept. So the graph at 4 touches. At negative 3, it bends. And at 1, it crosses or goes through, whichever terminology you want to use. So if it touches, that means that I'm just going to look at, for multiplicity, I can just look at the exponents now. 2, 3, and 1. And there's my degree, my multiplicity is there. Here's what happens with the graph, because sometimes it won't be so cut and dry, but the multiplicity is 2, 3, and 1 because it is the degree of the factor. Okay. Number of local extrema, in other words, max and mins. A polynomial function of degree n has at most n minus 1 local extrema. So if it's degree 3, then it could have 2 extrema. If the degree is 4, then it could have 3 extrema. Okay? In other words, 3 max and mins total, not 3 maxes and 3 mins, but 3 of them total. Inflection points. Remember we talked about points of inflection. Well, if it has the degree is n, then the number of inflection points would be n minus 2. And that really should make sense to you because every time we have a, so if I had this one here, okay, the highest degree, or this would have to be an even degree, the smallest it could be would be degree 4 because it has 3 extrema, which means then that there would be 2 inflection points. Okay? So degree is n, has to be greater than 2, so it has to be at least a quadratic, right? And then it would be at least, there are at most 2 inflection points. Okay? So they want us to talk about complete graphs. So here we have this function, so we're going to graph it, and they want us to find the smallest window that the graph will fit in. So go to my y equals 3x cubed plus 21x squared minus 40x plus 10. Okay, and I'll start with my standard viewing window of zoom 6. And now, this is a cubic function. So with the cubic function, I should be able to see at most, okay, 2 extrema and 1 inflection point. And possibly 3 zeros. Right? So let's look at this graph. Now, I can see a 0 here at about -8, a 0 around 0, and 1 at 1. So I do see the 3 zeros, okay, but I only see 1 extrema. Okay, I only see this minimum down here between 0 and 1, around there. So I need to find the max. So I'm going to need to change my window so that my y max is larger. So let's try 50 and see what we get. Okay, 50 is not even close. But I know that it's probably somewhere between, about in the middle between 0 and 9, -9. So if I actually go to my table, it'll help me to get there faster. Because here's the, let's look and see where the max value is here. The highest value I see here is 360. Okay, so I might try to go up to 400 for my y max. And that's not even far enough. All right, so let's try it again here. Oh, we got to miss something. Oh, I did. I put 40, not 400. And graph. Okay, and so now we can see our max, we can see our min, okay? But we can actually cut this window off a little bit. We don't have to go all the way to +10. So we could actually put the, our x max could be at, we could go to 5. Okay. And here now I can see the whole graph. I can see that it's going down to the left. So let's take a picture of it. I can see the complete graph here, and here is my window that's getting me that complete graph. So here's the window. Oops. Here's my window that I'm going to use then. And here's the graph. It shows all the important features. It's a cubic function, so I can see my max and the min. And I can see that it goes down to -infinity because this graph is going to continue down here. and continue up there to positive infinity because there's a positive leading coefficient. And it's going to have one inflection point where it changes from concave down to concave up. Okay, so let's look at another one. It says find this complete graph. Okay, now, thing is that let's talk about two things here. This is a quartic, so it's fourth degree. So that means that this graph, because it's fourth degree, it's going to, with a positive leading coefficient, it's going to look something like this. So there's going to be two max, probably two mins and a max here. And so we need to find a window that shows all of that. Why do I know that? Because it's positive leading coefficient, even degree, the end behavior is going to go to the ends. So let's graph it. X to the fourth minus 3x squared plus 5x minus 30. Okay, and we'll hit zoom 6. We'll go back to our standard viewing window. All right, let's see what we got here. Okay, now, with x to the fourth power, we would expect to see, possibly see 4 zeros, but in this case there's only 2. Okay. But we know it goes up on both ends. So let's take a look. Let's go to our table then and see if we can figure out where our numbers are. So these keep rising to the negative, okay? But we've got, let's see, we go down here to negative 37, looks like it's the smallest number there. And then they're going back up. So we need to go down to about negative 40, so let's try that. So our x min, we'll put it negative 40 and see what that produces for us. Comes down. All right, now, okay, we think it might look like this. It's not necessarily going to look like that, because from the screen you can see that it has a funny little style here. That this graph is fourth degree, okay, because it's doing some different stuff down here at the bottom, but it goes up on both ends. So my window here, though, for this, I can actually make smaller because my zeros are at negative 3 and around positive 3. So I could just be each side of them and go from negative 4 to positive 4, and here I can still see all of the important features of this graph. So here's my window then that would show me all the important features of the graph. Okay. So there we go. So we want to be able to, when we're doing a complete graph, we want to make sure we see everything there. So no polynomial graph of a function greater than 1 contains horizontal line segments. So if you ever see any horizontal line segments, then you have to do a little bit of work with them. Okay, we have one more example to do. We want to find a complete graph of this polynomial, and it says determine if the graph shown in figure 3.9a is a complete graph, and I don't have that. Okay, so let's go to the teacher's edition, and right, 3.9, example 3, example 4, example 4. Here we go. A little off. All right, here we go. Sorry. Okay. Okay, we want to know if this right here, figure 3.9a, we want to know whether this shows a complete graph or not. Okay? And here's the thing, all right? And this is all determined by, so I look at the graph here, and is it a complete graph or not? Okay. Well, how do I know? We need to check on the degree and compare the leading coefficient and the number of extrema. So we need to know those three things. All right. In this case, the degree is 5. The leading coefficient is a positive 0.01. And the number of local extrema then, it could have 4 extrema. All right. Since it's degree 5, it could have 4 extrema. Okay. Well, we see the 4 extrema. We see that there is 1, 2, 3, 4 zeros, but there could be 5 zeros. So I'm not seeing the 5th zero there. Right? But since it's degree 5, since we have degree 5 and the positive leading coefficient, the graph must look like this, where it must go down to the left and up to the right. Well, if I look at this graph, it's going up on both the left and the right. So this graph actually has to come back down over here somewhere because it's a odd degree leading coefficient of 0.01. So if I put this in my calculator, I would need to look to see if there's a 5th zero down here past -10. Okay? So when you're asking whether that's a complete graph or not, you have to look at degree, leading coefficient, and the number of extrema, specifically degree and leading coefficient, because the degree tells you whether they're going to go opposite directions if it's odd, same direction if it's even. The leading coefficient just tells you then where it starts and where it should end then for that.